Welcome to EGME-333 Fluid Mechanics. In this video, we're going to be discussing solving implicit equations using iteration. One of the most important computational problems is solving the roots of a function f of x, where we solve for x such that f of x is equal to 0. In this case, x is considered the root of the function f of x. This has many applications in multiple fields such as physics, engineering, and chemistry. Specifically in the field of fluid mechanics and in EGME-333, we see this with the Colebrook-White equation for solving the friction factor inside a viscous pipe flow. In this equation, F represents the friction factor, RE represents the Reynolds number, capital D is the pipe diameter, and epsilon is the surface roughness. As it's written, the Colebrook-White equation is an implicit function, meaning that we cannot specifically or directly solve for the variable F, the friction factor. If we rearrange the equation in this manner, then we can envision the Colebrook-White equation to essentially be a root-solving problem, where for a given Reynolds number and relative surface roughness, which is the ratio between the surface roughness epsilon and the pipe diameter capital D, the roots of the function capital F will correspond to the friction factor little f. So the question then becomes, how can we solve for the roots of a given equation? One common method for solving the roots of a function is the bisection method, which solves for the roots of function f of x by starting with two guesses, a and b, such that the product of f of a times f of b is a negative quantity, so the product must be less than 0. To envision this condition, note that f of a is a positive quantity and f of b is a negative quantity. So if the function f of x is continuous, then at some point within the range fb, the function must pass the x-axis, and therefore a root of x exists within the interval ab. Essentially, the bisection method uses a binary search algorithm to narrow the interval AB until it converges to the root contained within AB. The basic approach of the bisection method follows these steps. First, we compute the midpoint C between A and B by taking the average quantity between the two values. Next, we test if C is a root of f of x, such that f of c must equal 0. If c is not a root of f of x, then we have to check if the product of f of c times f of a is less than 0, or a negative quantity. If this is true, then we set the value b equal to c. Otherwise, if the product of f of c times f of a is greater than 0, a positive quantity, we set a to equal c. So to illustrate the bisection method, let's consider the function f of x, which is shown with this blue curve. We'll select a such that f of a is a positive quantity, and we'll select the point b such that f of b is a negative quantity. Given that I now satisfy the condition that f of a times f of b is a negative quantity and that the function f of x is continuous, I can argue that then there must exist a root contained between the interval ab. So let's implement the bisection method. First, we can compute the midpoint between a and b, and we set that value equal to c, shown here with the red point. Next, we can compute f of c and test whether or not f of c is a root. Note that in this situation, f of c is not a root, so we can determine the value of the product f of a times f of c. In this case, since f of c is a negative quantity, then the product f of a times f of c is also negative, so then we would have to update b to equal c in this fashion. So again, we can start a new iteration. So we'll again compute the midpoint between a and b, which we set equal to c. Then we compute the new value for f of c and check whether or not f of c is the root. Given that it's not the root, we'll highlight that in this case, the product of f of a times f of c is greater than 0, a positive quantity. So under this condition, we update the value of a to equal c. Now note that after 2 iterations, I have narrowed the interval a, b. And essentially, we can continue this iterative process until the method eventually converges to the root, where f of x is equal to 0, shown here in red. Lastly, let's illustrate how to utilize the bisection method by applying it to the function f of x such that f of x is equal to x cubed minus 6x squared plus 11x minus 6. We'll select the interval 2.5 to 4 such that a would equal 2.5 and b is equal to 4. Again, in this example, f of x is equal to x cubed minus 6x squared plus 11x minus 6. So we'll begin with iteration number 1 by first computing the midpoint between a and b, where again c is equal to a plus b divided by 2. Given that a is equal to 2.5 and b is equal to 4, the sum of those two quantities divided by 2 yields a value of 3.25. So this becomes the new value for c. Once we have the value c, we test whether or not c is the root of the function f of x. When we plug in x equals 3.25 to the function f of x, we get a value of 0.703125. Clearly not the root of the function. So we must determine, do we update the value a or do we update the value b? In the following step, we test f of c times f of a. And in this case, the product of f of 3.5 times f of 2.5 yields a negative quantity. Therefore, we'll set b to equal c, so the new value of b becomes 3.25. So this completes the first iteration, and we move on to iteration number 2 with a new updated range for a, b. So again, we'll start the new iteration by computing the new midpoint c between a, b. So again, c is equal to a plus b over 2. So we take the average of 2.5 and 3.25, which gives us 2.875. We test again to see if this new value c is the root of the function f, where f of 2.875 is equal to negative 0.205078125. Again, this is not a root of a function, so we have to update the interval a, b. So we test to see what the value of f of c times f of a is equal to. In this case, the product of f of 2.75 times f of 2.5 yields a positive quantity. So we update the value a to equal c, so a's new value is 2.785. So we can continue iterating through this method until eventually, with enough iterations, the method will eventually converge to the root x equals 3.